Okay, welcome back everyone, our second week. As I was saying during the break before people joined, homework 1 and 2 are already on the Moodle. They're both for submission after Pesach, but homework 1 has a specific question which involves measuring the moon. And you can only do that during particular days in the month where the moon is close to full. And that's about a week and a half from now. Actually, the best time to do it is on the eve of Pesach, the Seder, or a couple of days before or after. So plan to do it around that time. Don't postpone everything to after the holiday because you will not be able to do it later. Astrophysical and astronomical observations are not always at our convenient choosing. We have to do them when those objects are visible to us. So last week we did the first part of the historical part of this course. That is mostly the ancient and classical history and we started with the Moon, Earth, Sun system and the synodic conjugation or the synodic meetings in the relevant phases between the Earth, the Moon, and the Sun, which were known from antiquity. And we showed how even just using the Sun, the Moon, and the Earth, we can learn something new and interesting about the Earth itself. We learned that the Earth was a sphere or close to a sphere. And we saw how that was known and calculated early on, almost or even more than 2,000 years ago, including a calculation and a measurement of the radius of the Earth, the circumference and the radius of the Earth. So they did not only know that the Earth was a sphere, but they knew just approximately, to very good accuracy, what the radius was, so how spherical it actually was. Today we'll continue the second part of the history, reaching into modern times, and then we'll transfer to new things that are kind of more recent in astronomical observations. Some of them you might be less familiar with than the fact that the Earth is round, and even move on to observations, modern observations of other stars, stellar systems, and start to know our solar system and our neighborhood of the solar system and our stellar neighborhood. So we start, as I said, with the continuation of what the classical universe was, what they could measure and think that the universe looked like way back when. Well, put this on the side. Okay. Again, any questions that you have, just jump in, audio, chat, anyway, any position, language, or thing, any method that you want, I'm here. So we talked about the questions that were still open in addition to just the sphericity of the Earth. And we'll talk today mostly about the first one, orbits of stars and planets, or knowing planets and stars around us. So these are the ancient models of the universe as people in ancient Greece and subsequently in the Arab and Christian world, so Europe and the Middle East, thought of the universe. And there were different models. Not everyone thought that the Earth was at the center of the universe, although that was the prevailing idea, and that's represented here on the right side in what is described as the geocentric models. So geocentric, the Earth is at the center, and this was basically the view of the universe established and prevalent from approximately the 6th century before the Common Era, from Anaximandros, who did this model of the spheres, the spheres of the skies. In Hebrew, they would later be called the klipot, with the Earth at the center. The stars at that point they thought were the closest to the Earth because they revolve with the Earth. We see their revolution in a 24-hour period, followed by the Moon, which has a period of about 1 month. And we discussed the difference between the synodic months, the sidereal months, and other types of cycles of the Moon. And after that, the Sun with a period of 1 year. This model was built upon and expanded to the time that it was consolidated basically as dogma and as the model of the universe by Aristotle, approximately in the year 330 before the Common Era. And this is the model that, the classical geocentric model that we all grew up knowing people once held, with the Earth at the center, surrounded closely by the moon, then the inner planets, Mercury and Venus, then the sun. So they could already distinguish between Mercury and Venus as inner planets, which are closer to us than the sun. Today we know that they're only sometimes closer to us than the sun. As opposed to the outer planets, more remote from the sun, Mars, Jupiter, Saturn. These were the three that were known at the time. And then the fixed stars, which were taken to be very, very far away. But concurrently to these geocentric models, there were other models that they considered, starting from Philolaus of the Pythagorean school, who already displaced the Earth from the center. He posited that there was some fire, some heavenly fire at the center of the universe. The Earth would revolve around that central fire with a period of 24 hours. The sun would revolve around the central fire with a period of 1 year. This model explains night and day, because in the Earth's 24-hour period, there's always a time where the inhabited side of the Earth, would be facing the sun, so that would be day, but there would be a time when the inhabited side is facing away from the sun, and so it would be night. And it also explains, of course, the 1 year period of the sun in relation to the Earth. So basically the seasons, or some proxy for the year that we see. And this was even before Aristotle. This is a very old model, which was developed on, but sadly not widely accepted. It did give birth to an important family of models, namely the heliocentric models. The heliocentric model is also quite old. It did not start with Copernicus in the Renaissance. It actually started with Aristarchus of Samos 250 years before the Common Era. And he correctly put the sun at the center of, well, at that time, what was the universe or the solar system, followed by the inner planets, Mercury and Venus, the Earth, which is only surrounded by one satellite or natural satellite, which was the moon, and then the outer planets, Mars, Jupiter, Saturn, and the fixed stars far away. People didn't really like the heliocentric model, and for a very long time, even people who were dissatisfied with the geocentric model realized that the Earth could not be actually at the center, used a family of mixed models or dual models. The first of these was Marcianus Capella around the year 420, and he had basically the Earth surrounded by the moon. The sun was orbiting the Earth, but all the other planets were orbiting the sun. And this model, of course, is a great improvement on the geocentric model. It explains why the inner planets, so Mercury and Venus, sometimes appear closer to us than the sun. We can even sometimes see them transiting in front of the sun, and sometimes are blocked behind the sun or further away from the sun. And that happens because if they orbit the sun, then when they are on the opposite side of the sun relative to us, we will see them or not see them because they're blocked on the other side. So in Marcianus's model, the inner planets were orbiting the sun. For the outer planets, he didn't really have that problem, so they still orbited the Earth. So this is a dual model. Very, very similar to the model of the modern model of Tycho Brahe of 1588. Tycho observed with great accuracy the planets in the solar system, realized that the Aristotelian model, the geocentric model, could not be entirely correct, did not go as far as Copernicus with putting the Earth at the center of the entire solar system, but also used a dual model where some of the objects orbit around the sun, but the sun itself still orbits around the Earth. So on these previous plots, you might see some unknown figures. The markings for the different planets here, Mercury, Venus, Mars, Jupiter, Saturn, etc. These actually follow traditional signs in what was then astrology and now astronomy. And these are still used when one discusses the solar system or other objects. So here they are in plain sight. The most important ones, of course, are the Earth. We discussed the Earth, the circle with a cross representing the Earth. The Sun here on the left is a circle with a dot in the middle. Venus and Mars, you probably know from the female and male forms. Mercury represents the sign of the god Hermes. The moon is obviously the crescent shape of the moon. And Jupiter, Saturn, Uranus, Neptune, and Pluto, the modern planets, have their own signs. Oftentimes you would see, instead of the names, these signs on charts or even in equations. Mostly the mass of the Earth and the Sun would appear with the proper signs and not with the names. So you should at least remember that these exist. Okay, so the observations of stars, or rather planets, on the background of stars from the time of Aristotle started leading to some issues. And the issues are that the planets do not all seem to orbit nicely around the Earth in perfect circles, which is what Aristotle thought. So here we have an animation of a view of the sky. I'll start the animation shortly. You can see that it's centered basically around the ecliptic plane. As we discussed last week, the ecliptic plane is the plane in which the Earth rotates around the Sun. That when the moon crosses that plane, an eclipse is possible. So that's where the name ecliptic comes from. And because the solar system is almost entirely flat, it's basically close to a disk, all the planetary orbits are very close to the ecliptic plane. So for planets, we'll always be looking near the ecliptic plane. And another thing that's along the ecliptic plane are the 12 constellations that you know as the zodiac, or Galgala Mazalot, the 12 signs of the year. And of course, the reason we're interested in those particular 12 constellations along the ecliptic is because the sun can rise or set on the ecliptic plane. The sun is, by definition, always on the ecliptic plane. It's not in the same position throughout the year because the Earth moves around it. So the angle to the background changes. And that angle basically determines what time of year it is or what month it is. Basically, where is the sun relative to the stars? Not any stars, the stars on the constellations along the ecliptic plane. And if we play this little clip here, we'll see that this planet, which you can recognize as Mars, right? This is the sign of the male sign, so it represents Mars. For short periods of time, the planet seems to go backwards. This is called retrograde motion. In Hebrew, nesiga. In astrology, it's often called nesiga. And it means that if you look at the sky night after night, for most of the time, a planet would be moving forward in some direction. But sometimes we can see it loop backwards and do these retrograde motions. This is a problem for the Aristotelian model, for all the heliocentric models, the geocentric models, because if something orbits in a perfect circle around the Earth, the angle should always be growing. It should always be with a positive angular velocity. It should just be increasing in angle along the sky. It should never be going backwards. So this posed maybe the first substantial challenge to the Aristotelian model. Any questions thus far? None. Okay. The solution to this, proposed by Ptolemy, and this was accepted for about 1400 years, at least in the West and Europe, was to add what is called epicycles, or to add double circles for the orbits of the planets. So in Ptolemy's model, the Earth is still in the center. It is still a geocentric model. The moon orbits around the Earth. You can see here the period of rotation as 27 days in the third, or 27 days and 8 hours approximately. So obviously this is already the sidereal period and not the synodic period. They had good enough measurements to realize the correct period of the moon around the Earth relative to the stars. We have the sun in the third shell, or the third sphere, the third klipa, rotating around the Earth with a period of 1 year. We have the inner planets rotating on double circles. So they both rotate around the Earth with a yearly period, but they also rotate around that rotation with periods which today we know are the actual rotation periods around the sun of 88 days and 225 days for Mercury and Venus. And the same goes for the other planets, Mars, Jupiter, and Saturn. They all have the main cycles, which are at the length of more than a year, about 2 years, 12 years, and 30 years for these planets. But each of them also rotates with a 1 year period around the point that orbits on the main cycle. So they basically put one cycle on top of another, or compounded cycles, if you want to think of it in functional form. Then there's application of a function of position on top of a function of position. In this way, Ptolemy could explain why the orbits did not seem to behave just as perfect circles. Today, we would understand this is actually coming from the ellipticity of the orbits, and of course, from the sun being at the center. But he could avoid moving the Earth from the center and replacing it with the sun by these minor cycles. So this is a classical example, maybe the classical example, of better measurements and more accurate measurements and more complicated models actually hiding and interrupting better physical understanding of what was going on. What today we would think is obvious, that the sun should be at the center, and that if every object in your system has a minor period of 1 year, then maybe that 1 year is actually the main feature of the system, and whatever moves in that period, namely the sun, whose only period is 1 year, should be the focus of your analysis, and your model should be built around that, and not trying to fidget things or to do an to overcompensate and complicate the model to explain your data. So this was an excellent predictive model. He included all the main effects, and he could actually mathematically give much better results than any other model. In fact, better results than Galileo's and Copernicus's heliocentric models when they came up with them. Ptolemy's model is better at actually predicting where planets would appear. But it does that better just because it has more free parameters. It has circles on top of circles. And so if you want, it's been fine-tuned to our solar system, but it has less understanding and physical insight of what's actually going on. Okay. Ptolemy's model and Aristotle's model were accepted as scientific and religious dogma in the West, in Christian Europe, and also in most of the Muslim world for over 1,000 years. Here we have examples from Nachmanides, the Ramban, and in the next page we have Maimonides, the Rambam, accepting exactly the spheres and the wheels that Aristotle and Ptolemy attributed to the universe. Back then, all the universe, so the sun, the planets, the earth, and what was expected to be the fixed stars far away surrounding everything. At the same order, the same names, the same periods, basically accepted from Ptolemy's time onwards, almost without challenge. At least in Europe, it was accepted completely without challenge. Okay, here we have, again, the end of the Middle Ages, or the height of the Middle Ages in Europe. This is illustrations of Dante's Divine Comedy. We have the Earth as a sphere at the center of the universe, surrounded by the spheres of the Moon, Mercury, Venus, the Sun, the outer planets, and finally the stars far away, and the primum mobile, that which moves all the stars and all the heavens in their place. Accepted here in artistic form, painted on cathedrals. This was what people believed for about 1,000 years. The Earth is spherical, but it is at the center of the universe. or was expected to be. Here we have an interesting specimen, an interesting historical representation. It's called the Fra-Mauro map from 1450. And it shows us two main things. One is that, of course, the Earth was already taken to be a sphere. And we can see that for parts of it that they actually knew quite well, Europe and the Mediterranean Sea, the coast of Africa, the Black Sea, are actually quite accurate. And if we compare it to a modern satellite image of the Earth at the same angle, we see that this European Mediterranean area is even represented well. They knew the geography, they knew the sphericity of the Earth, and they could calculate these things very well, and they could even project from the radius how big the Earth is expected to be. And to scale, this is actually a very good representation. Remember that this is 1450. This is before Columbus, before crossing any ocean, before discovering the New World, the Americas, Australia. So already a very good representation. But still, this spherical Earth, represented here in the corner on the top left, is at the center of the universe, with all of these shells surrounding it spherically from the inside to the outside. Also, we see on the right, and we'll talk about this in the next class, the four elements that they expected to follow the same order. So Earth in the middle, followed by water, fire, and air. We'll talk about how that basically gave birth to modern chemistry and physics after Pesach, when we talk a little about quantum mechanics and how they come out of this. So just to summarize what we had, the classical view of the universe, the Earth as a sphere at the center, the moon around it, already with the correct period, 27 days and 8 hours, the sidereal period, the inner planets, the sun, the outer planets, and the primum mobile, and the stars on the outside. This is the classical view of the universe. At that time, the entire universe was expected to be represented in this figure. Questions up to now before we shatter the worldview? None so far. Okay. So today, of course, we know that is not the way the solar system is built. The modern solar system view is starting to get shaped in the Arab world during what in Europe is the Middle Ages, alternatively called the Dark Ages. In the same time, in the Arab world, which extends from basically Afghanistan to Spain, people are starting to raise questions. People are viewing the stars with better accuracy, and they're following planets with better accuracy. And the Ptolemaic model doesn't seem to work anymore. It starts to slip. It starts to give predictions which are not verified by observation of the actual positions of planets as the centuries progress. Different people start by trying to complement or modify the Ptolemaic system. Here on the left, on the right side, we have a model with the Earth at the center, but now with 3 levels of cycles. So the 2 circles that we had from Ptolemy, and also a 3rd cycle, trying to correct for the accumulated errors and the better accuracy of observations by adding another degree of freedom, basically, by trying to make the model even more complicated, but still using the same element, which they thought was the only one that was relevant, which was perfect circles. So they still think the symmetry of nature dictates that all orbits have to be spherical, have to be circular, but you can add one circle on top of another circle to kind of get away with that restriction. Basically what they were doing, they were emulating ellipses. You can think of an ellipse, and I think I put on the Moodle code that actually shows that. You can think of an ellipse as a circle at the radius, which is the average of the semi-major and semi-minor axes, on top of a smaller circle, which is the difference between the semi-minor and semi-major axes. So the eccentricity would actually come into play by introducing this second circle on top of the first one. And mathematically, geometrically, these two descriptions are completely equivalent. So basically, you can fool yourself, or you can try to maintain this circular orbits by compounding one circle on top of another to explain your observations without replacing what is in essence the fault of the model, which is the sun being at the center rather than the Earth, or in your case, in their case, keeping the Earth at the center instead of the sun. They also notice other things that would later bring forth the collapse of this model. As we mentioned before, inner planets can be seen transiting or coming between the sun and us. We can see them kind of as a small black dot crossing across the sun. And that transit immediately tells us that that planet is between us and the sun, so it's closer to us than the sun. While at other times, it can be seen to approach the sun and then disappear behind it, meaning that it's at some point further away from us than the sun. A problem in the geocentric model that can't be accounted for even with these circles on top of circles. They also start looking at in greater depth and greater perception at the Milky Way, that band of kind of milkish white light across the sky, known from ancient times, and they start noticing or proposing that it's further away than the regular stars that we see, and even that it might be composed itself of many, many stars that are just kind of blend into each other at the distance. They raise the possibilities that the Earth itself is not fixed anymore, that it revolves, that it moves. They even noticed the approximately 1% discrepancy in the distance between the Earth and the sun, which they, of course, can measure by measuring the angular size of the sun. If the sun is of different angular size, then unless it pulsates and changes in size, which is less probable, that can be related to the distance between us changing. So they realized that if distance is not fixed, the orbit cannot actually be circular, and they start proposing that planetary orbits could actually be elliptical rather than circular, a huge digression from the Ptolemaic and Aristotelian model. This happens in Iran around the year 1000. In the next few hundred years, they also establish stellar observatories. Some of these actually have the best, or had the best tabulations and maps of the stars and the planets and their orbits, well into the time of the invention of the telescope in the West. So approximately 400 years after their establishment, still the best stellar and planetary tables in the world. And we have this period in Spain, what was then Andalusia, Al-Andalus, where there's actually you call it the revolt against the Ptolemaic model. They start bringing all these ideas that say that actually Ptolemy's model is not supported by observation of the stars and the planets. And they start proposing heliocentric, or models that they at least suggest that heliocentric orbits can explain the data at least as well as the geocentric, Ptolemaic, and other models. So these are Qutb Shirazi and Ibn Shatter, basically the first people to repropose a heliocentric model after the time of Ptolemy. We have good reason to think that Copernicus was exposed and knew of some of these proposals and some of these research papers and books developed in the Arab world, imported into Europe through the Byzantine Empire, through the collapse of the Byzantine Empire. And of course, as we know, Copernicus, this is the part of history where, again, most of you probably already heard, proposed the first official Western heliocentric model. So putting the sun at the center, surrounded by the inner planets Mercury and Venus, the Earth is only the third planet from the sun, no longer in a special privileged position in the universe, and the outer planets following from there outwards. This was a great revolution in the West. It took about 100 years to actually be accepted and vindicated. During those 100 years, there were clashes with the church. Tycho Brahe, who we mentioned earlier, tried to find middle way by proposing a mixed model, a dual model, which we mentioned, with the Earth at the center, but the sun surrounding the Earth and the planet surrounding the sun. So kind of a mixed dual model which tries to appease both sides. Giordano Bruno was the person who actually paid the price for supporting the heliocentric model. He was burned alive in Rome after preaching that the sun the Earth was not at the center of the universe, but perhaps the sun was at the center of the universe. And actually, more than that, he proposed the idea that the sun is not the only star in the universe, that all the stars that we see are sun-like, and that some of them might have planets around them just like our Earth, and that some of those planets might have civilizations on them with peoples on them, not just us on the Earth. And he went on to say that those other planets must have their own version of God and Jesus and all the Catholic Church. And for that, he was declared a heretic and burned to death. But more prudent political scientists at the time, like Tycho and Copernicus, did find a way to promote their ideas and publish them and to scientists and to the general public without getting burned alive for it. And Tycho, in particular, was an advisor to the emperor, the Holy Roman Emperor, in Prague. He was chief advisor, chief astrologer to the royal court, the imperial court. Lived out his life in the palace, basically, and could publish other things that conflicted with the Aristotelian view in safety. Among those were the first new star that he published in 1572, or observed in 1572. At the time, he called it a nova, which is a new star. Today, in modern classification, we actually call that a supernova. So we relate that to an exploding star at the end of its life. We'll talk about them more, I think, in maybe week 10 or 11 in this course. And he also observed the comet, the great comet of Tycho at the year 1577. And he could follow that comet night by night through the sky. Later, Tycho's mappings and measurements of positions of comets and planets would be used by Johannes Kepler to claim that orbits are actually not circular, but elliptical, which is what today we accept as the first order determinant of orbits of stellar and planetary motions. Okay. Galileo Galilei, which I am pretty sure you've heard of, or hope that you've heard of in mechanics or in popular science classes, provided a great advancement of this heliocentric view of our solar system. And he did so with new observations. He was the first person to use a telescope, which was just invented, for scientific work, so for astronomical observations. He built his own telescope quickly after finding out about the technology from the Siamese ambassador in Florence. The telescope was invented in Holland, or what is today Belgium. A report of the diplomats in Belgium, in Holland, reported it in Florence. He heard about it, built his own telescope, and pointed it to the sky. And then he discovered that the moon was not a perfect sphere. Again, kind of a break from the Aristotelian and Platonian view of perfect ideals in the sky. He found sunspots, dark spots on the sun, and was the first person in the West to document them. They had been seen and documented centuries earlier in China, but in Europe, he was the first person to notice sunspots. He discovered the rings of Saturn, was the first person to actually notice that Saturn itself is not a sphere, it has these, what he called ears or lobes on either side. Today we understand them as rings. He found in the Milky Way those individual stars and could actually tell them apart one from another. And he found 4 moons surrounding Jupiter, the largest ones. Today we know them as the Galilean moons, named after him. Io, Europa, Ganymede, and Callisto. And he could follow the periods of the orbits of those moons around Jupiter. Of course, the most important conclusion he drew from these Galilean moons orbiting Jupiter was that there are stellar bodies or objects in the sky, celestial bodies, that do not surround the Earth. They obviously revolve around something else. They obviously revolve around Jupiter and not around the Earth. And that in itself was enough for him to claim that if something can revolve around another object, then anything can revolve around another object. And that kind of said that the Earth could not be the center of the solar system, and adopting the sun as the center instead of the Earth was then the next logical conclusion that he drew. It was also supported by observations of Venus. What Galileo noticed about Venus, here encrypted in Latin, Cynthia figuras emulator mater amorum, or in English, Cynthia, which is Venus. The shapes of Venus emulate or look like, Cynthia is the moon. The figures of the moon are emulated by Venus, mater amorum, the mother of love. So Venus basically replays or reproduces the shapes of the moon. So the phases of the moon is what we discussed last week, and we all know from watching the sky. And as we discussed, it comes from the synodic configurations of Earth, Sun, and Moon, or Earth, Moon, and Sun. If Venus shows the same phases, then there are relative positions or synodic positions between Venus, the Earth, and the Sun. And again, that means that if you compare it to the size of Venus at these different phases, you can conclude that Venus itself revolves around the Sun, not around the Earth. And again, heliocentricity is the conclusion that he came to. Okay. As I'm sure you all know, the church does not accept this model as well. Galileo was ostracized, declared a heretic. His books were banned and for hundreds of years. He died in house arrest. He also became blind from using a telescope to watch the sun directly. Don't ever watch the sun directly. And his excommunication lasted basically until 30 years ago, when Stephen Hawking personally asked the Pope to release Galileo from his judgment. At the same time as Galileo, Johannes Kepler was making his measurements, or rather using Tycho's measurements. Kepler was assistant to Tycho until Tycho died. So he did his own measurements, but also used the decades of work collected by Tycho to propose his 3 rules, the 3 laws of Kepler. Who here has studied the 3 laws of Kepler in mechanics, and who hasn't?
I haven't.
That was 1 no.
I did.
Who has?
I think we did. Can't really remember.
Think you did, but don't remember. Okay. So in brief, Kepler gives new laws for orbits of planets around the sun. He understands the sun is at the center, or what Kepler would actually better specify, the sun would be at the focus. Because the first law of Kepler is that the orbits of planets around the sun are actually not circular orbits, they're elliptical orbits. So not perfect circles as everyone from Aristotle's and Plato's time had thought, throughout the Middle Ages and through the Arab world. Orbits would be elliptical, not perfect circles, but ellipses. An ellipse has two focal points, not just one center. And Kepler places the sun as heliocentric, but actually it's heliofocal. So the sun is at the focus of these orbits. And here we have an example, the Earth in an elliptical orbit, greatly exaggerated. It's not this eccentric, it has an eccentricity of about 0.01 or 1%, but approximately shown as an ellipse here. It has a major axis, which is the long diameter of the ellipse, and a minor axis, which is the shortest diameter of the ellipse. And they're not equal to each other. If they were equal, then it would be a perfect circle. So the first law says that these orbits are elliptical and not circular. This in itself did away with all of the epicycles and circles on top of circles and compounding complex geometrical shapes that Ptolemy introduced and that the Arab astronomers complicated even further, because we're back to a simple geometric shape, but that geometric shape is not a circle, it's an ellipse. So now you can explain why something is sometimes further away, sometimes closer. The distance between a planet and the sun can actually change along its orbit. The second law is the law of area and time. And that is the law that says that a planet, if you start a clock and measure a certain amount of time, then covering the left side here marked as A, an area A in a certain time, and covering a different part of the orbit B in some other time of the year or of the orbit, but of the same duration, the areas would be equal. So in a circle, this is no problem. In a circle, you have constant angular velocity and constant radius. And if you multiply those two together, you get constant angular velocity. What Kepler notices from Tycho's measurements is that the velocity of planets along the sky is not always constant. And he explains it and actually explains how to relate the angular velocity of planets at different parts of the orbit to their distance from the sun at that part of the orbit. So it's no longer the angular velocity or the radial velocity or the tangential velocity. None of those are constant anymore. But the product, which is basically r squared theta dot, which is the area. So r squared would give us dimensions of area, and theta dot would give us the opening angle. So we're calculating here the area of basically a slice of pizza, or a slice of the orbit. The area of that slice at per unit time, so the rate of accumulation of this area, that is what's constant. Today, and since the days of Newton, we know that this is basically just conservation of angular momentum. Angular momentum is the distance r times the velocity v. The perpendicular, it's a perpendicular product, it's a vector product. So you actually don't take the whole velocity, you only take the part of the velocity which is perpendicular to the radius. So that's the tangential velocity r theta dot. And so r times r theta dot is r squared theta dot. So in mechanics, you learn this as angular momentum or angular momentum per unit mass. But the conservation of angular momentum geometrically just means equal areas for equal times. So Kepler discovers this as his second law, basically discovers conservation of angular momentum. Any questions? Okay, so the first law is telling us that the orbits are elliptical. The second law tells us that for the same planet, for the same orbit, velocities change and distances change, but the relation between them, the angular momentum, is constant. The third law allows us to compare between different planets, orbits of different planets surrounding the same central object, the same sun in our case. And this is the ratio of distances, R1 to R2, and the ratio of periods, of durations of these orbital periods. So T1 and T2 will be the period of object 1 and object 2. R1 and R2 will be basically the distances, or you can think of this as either circular or close to circular, the semi-major axis. And he finds that the ratio of times of periods squared is equal to the ratio of distances cubed. And at the time of Kepler, this only included Mercury, Venus, Earth, Mars, Jupiter, and Saturn. So the first 6 points on this diagram below. Today, we know also Uranus and Neptune, and of course, Pluto off the chart, and other objects. And today, we find very accurately that all of these points sit on the same straight line. The straight line, which is a logarithmic scale, is a slope 3/2. So you go for every increase of a factor of 10 in period, that's a factor of 100 in period squared. So a factor of cubed root of that in the radius or in the distance. So there's a slope of 3 to 2, basically. Any question? Ken, yes.
שאלה קצת לא קשורה, אבל כאילו לפני שהם המציאו את הטלסקופ, איך הם ידעו להגיד מה המרחקים של הכוכבים יחסית לכדור הארץ?
So the question was how they could measure distances before they had the telescope. And the answer is that it's actually more complicated than that. They couldn't measure the distances even with the telescope, because as you'll find in your homework exercise, measuring the angular distance to the angular diameter of the moon, the angular diameter in itself still doesn't tell you how far away something is unless you know how big it is. It just gives you one parameter, and it doesn't tell you the distance. For the moon, you can solve that. It was a solved problem, and you'll also do this in your homework, because you can relate the radius of the moon to the radius of the Earth if you watch a lunar eclipse, where the shadow of the Earth on the moon allows you to compare the radius of the Earth's shadow to the radius of the moon and basically get an estimate of the moon's radius in units of the radius of the Earth. And as we did last week, measured the radius of the Earth from the angle of shadow of the sun, or angles of stars on the horizon and above it. You can basically find, at least in kilometers, the diameter of the moon. And if you find the angular diameter of the moon, you can divide those and find the distance to the moon. But that already doesn't work for the sun, because the sun is the same angular diameter as the moon, more or less, but obviously a different distance. So and we have no way of measuring a priori the kilometer or the length diameter of the sun. So we only know the angular diameter, but we don't know the distance, and we don't know the actual the physical diameter. So we know the ratio, but we don't actually know the distance. And that's even for the sun. Okay? So that means for, at least for the time of Kepler and for his contemporaries, and about 100 years or even 200 years after that, 100 years after that, all the distances of the planets were measured in what's called AU, astronomical unit. So it was measured in multiples of the distance of the Earth to the sun, which they didn't actually know how long it was, how big that distance was. On the next plot here, we show how to measure distances to planets in astronomical units. So we don't know how big an astronomical unit is, but we can measure in multiples of this unknown unit. And it goes a bit differently for inner planets and outer planets. So in the middle here, diagram A, we see a measurement of an inner planet, Venus, for example. So if this point P for planet represents Venus, E represents the Earth, so it's exterior to the orbit of Venus. The sun is at the center. Then we can take the distance of the Earth to the sun to be 1 astronomical unit. We don't know the distance to Venus, but we know that Venus shows phases. Like we said, phases similar to the moon. We know that Venus will show us exactly one half circle, one half of its phase, when it's at a 90-degree angle between the Earth and the sun. Because then the half of Venus which is facing the sun is illuminated. The half of Venus that is facing the Earth is what we can see, and the intersection between the half that's facing the sun and the half that's facing the Earth is exactly the 90 degrees that we can see, or one half of Venus.
אבל כשאנשים, לפני שהיה להם, כאילו בתקופה של קופרניקוס וכל האלה, איך הם ידעו מה החצי שפונה לכדור הארץ? הם ראו פשוט נקודה בשמיים.
At the time of Copernicus, they saw, they're not exactly dots, they're not points, they're actually a little larger than that. But yes, at the time of Copernicus, they did not see the phases of the planets. So they did not know the distances to the planets. They could only know the relative distances. They could figure which was closer and which was farther away. But they could not actually measure distances. Once they had telescopes and as Galileo did, see the phases, the face of Venus, then they could measure the distance to Venus, but only in multiples of the distance between the Earth and the sun, so in astronomical units. That's why all those historical depictions of the solar system, right? This one, for example, it shows the relative order of the different planets. So we have Moon, Mercury here on the left side, Luna, Mercurio, Venus, Sol, the Sun, Mars, Jupiter, Saturn. They knew the order at which these would have to follow each other, and they have very accurate measurements of the periods. So 27 days and 8 hours, and even fractions of an hour for the Moon. 70 days, 7 hours for Mercury. That's not actually accurate, but they had estimates. 273 days for Venus. They could measure the periods and basically order things by the period, but they could not actually measure distances until they started, basically until they had the telescope, and then they could see the phases and compare the angles, and from the angles calculate the distances in multiples of the astronomical units. Okay, does that answer the question? Okay, so here we have an internal planet or an inferior planet. We can wait until it's at 90 degrees, so exactly half phase facing towards us, and then we know 1 astronomical unit for the far side of the right triangle. We know the angle because we can measure against the stars far away the angle of the sun and the angle of the planets. So we know alpha. We know this side of the triangle C, and so we know that the distance r is basically C times sine of alpha. So this is now a trigonometric calculation, and we can calculate the distance of an inner planet from the sun in multiples of the side C, which we don't know, which is 1 astronomical unit. It's slightly more complicated for an external planet or superior planet, like Mars or Jupiter. Then we have to take multiple measurements with the Earth moving, calculate the different angles. If we know how much the angle is here between the Earth, the sun, and the Earth at a different time, the angle being the relative part or the fraction of 360 degrees subtended by the number of days between measurements out of 365. So we know this angle ES E prime. Then we can calculate the base of the triangle between E and E prime. And then if we measure the angles from E prime to P and from E to P, so the different angles at the base of the triangle, we can calculate the size of the triangle E prime P, calculate its height, and calculate the distance to the sun. So we can't directly measure still any of those distances, but we can do different angular measurements and distance measurements and time measurements from the Earth to calculate, at least in multiples of 1 astronomical unit, what are the distances to the various planets. Okay, questions so far? If not, let's take a 15-minute break and then continue with newer things. Okay, recording's back on. So as we discussed just before the break, measuring distances, even in the solar system, is not that trivial at all. Wasn't trivial when Kepler did it and still isn't. We could calculate distances between the various planets basically by inferring them from angles and from the basic elements that we did have. The only scales that we had, 1 AU as the average distance of the Earth from the Sun, which was not known at the time, and the period of the Earth around the Sun, which gives us a time and which we can use to calculate angles in the orbit of the Earth. I'll add that eventually calculating how long a single astronomical unit was, so an estimate of the distance of the Earth from the Sun, was only calculated at the end of the 17th century. It was done by Cassini. Today, telescopes and satellites are named after him in space missions. But the French astronomer Cassini, the way he did it was using parallax. Parallax with a baseline, which was the Earth. He sent his collaborator, multiple collaborators to different positions on the Earth. He was working from an observatory in France, and he had collaborators in Africa and in South America. So they could know from the radius of the Earth and the longitudes, the different distances between those points on the Earth. So they had distance measurements for the base of different points on the Earth, and they measured the angle to Mars from those different points. So the angle, the position in the sky of Mars relative to the stars far behind Mars, the slightly different angles that they measured from different positions, different continents on the Earth, could be used to find the distance between the Earth and Mars in multiples of the radius of the Earth. So in your homework exercise, you'll be calculating the distance between the Earth and the Moon in multiples of the radius of the Earth. And they used a similar method with parallax to find the distance to Mars in multiples of the radius of the Earth. And as we know, even from the time of Eratosthenes in Alexandria, we know the radius of the Earth from Earth-based measurements. If we follow the process described here in diagram B, which is finding, oh, I'm not showing the slides. Okay, I'm on the same slide as before, but let's see how to do it. Where are my controls? Share screen, slideshow. Okay, now do you see the slide?
Can.
Good. Okay, so as you can see, I'm on the same slide as before. So diagram B tells us how we can calculate the distance from the, for example, EP, so the distance from the Earth to Mars, some exterior planet, in multiples of an astronomical unit, which is the basis unit of measurement of distances in the solar system. And if we know then the distance between the Earth and the same planet in multiples of the radius of the Earth, we can find and calculate how big an astronomical unit is in multiples of the radius of the Earth. And that's what Cassini did. And for the first time since antiquity, actually found the scale of the solar system. And today we take 1 astronomical unit to be approximately 150 million kilometers. Much, much larger than what was expected. If we go back to this old worldview from Greece and Anaximandros, we see they expected basically the sun, the stars, the moon to be about 30 times farther away than the radius of the Earth. That was kind of the hand-waving estimate that they had. So obviously 150 million kilometers is a lot more than that. And that gives us the scale. Another thing we have from Kepler's time, even without knowing the distances themselves, this comes immediately from Kepler's third law, the ratio of, or the relation between distance and time, an orbital period. We have an explanation of the retrograde motion of stars or a planet in the sky. The way that it works is that we can find here, we take 5 times, 1, 2, 3, 4, and 5, and we look at the positions of the Earth, marked with T for terra, the Earth at 5 different positions, so about half a year in Earth time. And schematically, we take 5 points in time for a planet, say Mars, the same 5 points in time, P1, P2, P3, P4, and P5. Now, the angle that an observer on the Earth, at which an observer from the Earth sees the planet against the sky, so against the stars far away, which hardly move at all or don't seem to move, is obviously the line that connects the Earth to the planet. So we see that at time 1, the line from T1 to P1 reaches position A1, which is the most extreme on the bottom. At time 5, it reaches the top, position A5. So that's fine. That would be seen as a progression of the planet against the sky. It moves in the same direction. But in between, at times 2, 3, and 4, we see that because the planet is much closer than the stars far away, and because the Earth is rotating faster than the planet, because it's in a more interior orbit, so the period is closer than for the outer planet, with the same ratio of periods squared equals the ratio of radii cubed. So the outer planet moves slower, which means that the angles look different. See a question? What is in the positions A? Fixed stars. Yes, the sky. Basically, if we look at, what was our diagram of retrograde motion? Here. This was our retrograde motion. We can aim our telescopes, or just our point of view looking at the sky, and we can always find that basically the same stars appear. Here we have the constellation of Aquarius, one of the 12 constellations of the zodiac. The main stars are marked here in the blue line, connecting the stars in the constellations, so Delta Aquarius and Lambda Aquarius and other stars in the constellation. And we can mark the different positions of a planet like Mars against the sky. So these would be the angles A that we measure. The angle that we measure is basically relative to the same stars on the background. And the stars don't seem to move in the background. We take them to be fixed. If you want to be more accurate, you can do this at the same time of day every night. So then the rotation of the sky as well is the same. So you can have a consistent measurement, and you follow the different angle that the planet marks against the background stars. And that angle goes in retrograde motion. So most of the time it goes forward, but sometimes it will go back. So we have the angle A1, then A2, backwards to A3, backwards to A4, and only then forward to A5. So that is retrograde motion. It's because the inner planet, Earth, is rotating at a different angular velocity than the outer planets, and so the angles on the fixed sky far away are different. Okay. Any questions? Okay, so that's retrograde motion, and it comes directly from Kepler's laws. Okay, so we already discussed measuring distances in multiples of an astronomical unit and of Cassini calculating how much an astronomical unit was. And with these measurements, we come finally to the age of Newton. And Newton is the first to give not just geometric explanations, or rather geometric descriptions, but to actually give mechanical explanations. So this, obviously, you know from mechanics, the laws of Newton, F equals ma, forces mass times acceleration. Newton's law of universal gravity, not written in this form originally, but today we take it in this form. Some constant, Newton's constant g, times the product of the masses divided by the distance squared. An attractive force between any two objects in the universe. And these two laws are enough to explain basically all of Kepler's results. So this is about 80 years after Kepler, but now enough to actually explain them or derive Kepler's laws, not as an observational assumption or not an observational inference or result, but as a calculational result. So from basically first principles from Newton's laws. And the calculation is very simple. We mark the, for circular motion, we can ignore ellipticity because it's not very significant for the third law, although we can, of course, Newton explains the ellipticity itself, as we said earlier, as conservation of angular momentum. That's the second law, and the first law together, the ellipticity and the velocities along the ellipse. Newton also moves the center of the orbit, the focus of the orbit, no longer exactly at the sun, but at the center of mass between the sun and the planet. So it's a slight correction to Kepler. The sun is not really at the focus, it's not really heliocentric or heliofocal, but the focus is at the center of mass between the sun and the planet. Except that the sun is much, much heavier in mass than any other planet in the solar system. It's about 1,000 times heavier than Jupiter and much heavier than any of the other planets. So for Jupiter, the center of mass between Jupiter and the sun is just outside of the sun. For all the other planets, it's well within the sun, so internal to the sun itself. So heliocentric is a good approximation, and Kepler actually got that basically correct. So that's the first and second laws. For the third law of Kepler, we need to relate orbits of different planets in different radii. So we'll take it as approximately circular. We have the angular velocity as approximately constant, 2 pi divided by the period t. The force, on one hand, is the centripetal force, or the centrifugal force, depending on how you look at it. For circular motion, it's m omega squared r. But the driving force keeping the system together is Newton's universal gravity. G, big M will be the total mass. For all intents and purposes, just the mass of the sun, because as we said, it's at least 1,000 times heavier than the next sized planet. Small m would be the mass of the planet and the distance squared. Immediately, we find that the small mass cancels out. So the orbit doesn't actually depend on the composition of the planet. It only depends on the position of the planet, r, and the angular frequency, omega. Moving things around a bit, we find that the constant maintained in the solar system is gm divided by 4 pi squared. That is the same constant for all the planets and all the comets and every object in the solar system orbiting the sun will obey this same relation. And so we have this r cubed t squared relation of Kepler. And it's derived. We have it as a result of Newton's mechanics. And this is, of course, a great triumph for Newton. He can give two simple laws of mechanics, of physics, which explain all of the results of Kepler and basically finalize the debate and give the answer for all of the orbits of planets observed for thousands of years prior. Questions up to now? Okay. What is new about Newton's mechanics is that it can actually give us a lot more power and a lot more tools, many more tools than just the observations of the systems that we know of planets. In particular, it can give us more information about non-circular orbits. Some of them we already knew, the elliptical orbits, but also parabolic and hyperbolic orbits. And the way it's typically done, and if you haven't seen this in mechanics, say so, or if you have, then it should be familiar. We can define a potential, which is the integral of the force. The integral of gm over r squared is minus gm over r. And that's basically the gravitational well, or the gravitational potential centered, in our case, around the sun. And every object will want to fall or slide into this potential well. If we only look at the radial coordinate r, we can basically get rid of the angular, if you only look at the radial coordinate r, we can get rid of the angular coordinate theta and encapsulate it in this term, which is basically the angular momentum. So L is the constant angular momentum, and we said from Kepler's time that it's a constant. So we get a term that looks like, that has a plus sign and looks like L squared over R squared. What these mean separately is that we have, if we draw here the effective potential, so the energy or the potential going up, the radius going to the right, then we have this bottom curve, minus gmm over r, which is the Newtonian gravitational well, gravity. And on top, we have a positive potential and a repelling potential, which looks like a potential barrier called the centrifugal barrier or the angular momentum barrier. At very, very far distances, 1 over r is small, but still bigger than 1 over r squared. So on the right, we see that the gravitational part wins over. So far away, things look like gravitation, like gravity. But close to the object, when r is very close to 0 or very small, 1 over r squared is much bigger than 1 over r. So the positive part wins out, and we have that close to 0, it actually looks like the barrier. In between, we have this little dip, this part here, which distinguishes us now between different types of trajectories, different types of orbits for different types of particles or planets. Seen here on the left, we have, first of all, planets or objects which are below the 0 energy line. That means that they're trapped inside the potential well. Conservation of energy means that they always move on the same level, at the same height, between potential energy, which is extremal at the endpoints. And then the kinetic energy is 0, and they stop and reverse direction. So they go from some closest approach R min to some maximal approach or maximal distance R max. They go between, and these are the elliptical orbits that we know. Of these, there's a special orbit at the bottom where R is fixed, and that's the circular orbit, because the kinetic energy, again here only in the radial coordinate. So the kinetic energy is 0, which means the radial velocity is 0. So the radius doesn't change, it's a fixed radius, it's a circle. So we have a circular orbit at the bottom. On top of that, we have a basically infinity in planetary motion, an infinity of elliptical orbits, but it's not infinity all the way, because once we reach energy 0, the planet or particle is no longer trapped, it's no longer confined, it can go out to infinity, and that's a parabolic orbit. If we give a particle even more kinetic energy, so that its total energy is positive relative to infinity, then it's a hyperbolic orbit. It's an object that comes from somewhere on the right, approaches while slowing down all the time until it reaches some minimum, and then it goes back out again, a hyperbolic orbit. So planets are mostly are in elliptical orbits very close to the circular one, but we also have comets, which which travel on very, very eccentric ellipses. So not circular at all. They're much higher, still trapped, still confined. Total energy is negative, but they can have very, very long period, and R max can be much larger than R min. And we don't usually see this around the sun, but we can also think of hyperbolic orbits. That is, for example, if another star comes close, not close enough to be trapped, but close enough to have its orbit slightly change and change direction and continue off into infinity. So we have these 3, or if you want 4 types of orbits in Newtonian gravity. Any questions so far? Are these orbits that you're familiar with?
Perfect.
Yes.
We know these are theoretical, but have we ever encountered a pure circular movement?
A pure circular?
Yeah, the E equals the bottom of the well.
Okay, so obviously it's very hard to detect a single point in the parameter space of real numbers, or a floating point, or a number that can take anything, right? So would you consider 10 to the minus 10 to be exactly circular? Would you consider 10 to the minus 5 to be exactly circular, 10 to the minus 1? What would you consider as eccentricity that's small enough to be perfectly circular?
Oh, I see.
It becomes, in mathematical terms, it becomes something of measure 0. So something that you can always get very close to, basically as close to as you want, but it's very hard to say that something is exactly 0. It would almost never be exactly 0.
But by approximation, it's close enough to be considered sometimes circular.
Yeah, so in the solar system, like we said, the Earth's eccentricity is about 1% around the sun. We can talk about which others have slightly better or slightly worse, slightly larger, smaller eccentricities, but 1% is kind of an order of magnitude what we find in our solar system. If you look at other systems, not in the solar system, sometimes you can do better. We'll do this later in the course when we talk about general relativity and gravitational waves and black holes and things like that. Black holes are much more compact, and neutron stars and black holes basically are called compact objects. They're much, much smaller at the same mass. So a neutron star with the mass of our sun, or slightly over that, would be only about 10 or 20 kilometers in radius, as opposed to our sun, which is about 700,000 kilometers in radius. A black hole of the mass of the sun would be 3 kilometers in radius. So much, much smaller. That means that they can actually, 2 of those can get much closer to each other. Then gravity is much stronger, and there are other effects, emission of gravitational waves and other things, which would cause the orbits to circularize. So after a long time, you can actually consider it to be circular to a very good eccentricity, maybe 10 to the minus 10, 10 to the minus 20, very, very accurately. Still, nothing is ever perfect in physics or in the real world. If you're looking for a parameter of measure 0, you'll basically never find it exactly 0. Okay. Any other questions? Okay. So let's talk about the solar system. Here we have a model representation. You can find these, people like to make these posters because they're quite pretty. This is obviously not to scale, okay? That is, okay, you cannot reasonably make a model of the solar system where both the sizes of the planets and the distances between the planets are to scale. The reason for that, as we said, was that if the Earth, for example, has a radius of about 6,000 kilometers, and the distance between the Earth and the Sun is about 150 million kilometers, then you need about a ratio of several thousands between your resolution for the Earth and the resolution for the distance between the Earth and the Sun. I think I gave this as a homework exercise last year to construct how big would a model of the solar system have to be if, for example, the Earth was a small marble and you put it in the physics department of Bar-Ilan, where would you put the Sun so that it would be to scale? And the answer is a city or several cities away. So the scale here is a tricky issue. This does show the sizes of the planets to scale. So we see here the interior planets. Earth is the largest of them, but only slightly larger than Venus. Mars and Mercury are somewhat smaller. We see the moon here, quite smaller than the Earth. We see some of the asteroids in the asteroid belt, the outer planets, Jupiter, Saturn, and the new ones discovered in the last 200 years, Uranus, Neptune. Pluto today is not considered a planet, it's considered a dwarf planet. It's actually smaller than Sirius, it's smaller than several asteroids. But it occupies the Kuiper belt, which is another belt of many, many asteroid-like objects, some of them smaller, some of them bigger, at the outskirts of the solar system. We see the major moons of the planets. So Earth, of course, has only one. Mars has two planets, Phobos and Deimos. I think they appear in your tutorial or homework exercise. Jupiter has many, many moons. Here, I think it lists about 70 moons of Jupiter. But the four major ones are the Galilean moons we mentioned here in distance from Jupiter, Io, Europa, Ganymede, and Callisto. If any of you were fortunate enough to watch the conjunction in December, when Jupiter and Saturn were quite clear in the sky, you could actually see these four moons with any simple telescope. Okay, actually, like we said, the first telescope ever used for astronomy by Galileo already caught these four. So they're very easy to spot and quite pretty as well. Saturn with its rings discovered by Galileo and some of its larger moons. It also has many tens of moons. Uranus and Neptune with their many, many moons, and in the Kuiper belt as well. Pluto is not a solitary object. Pluto itself has, I don't remember now if the number is 3 or 4, companions. Used to be considered moons. Charon was the biggest of them. No longer considered as moon of Pluto because they're almost the same size. So neither of them is now considered a moon or a planet, but they're both considered kind of dwarf planets or dwarf objects in the solar system. Here below, you have a table of the standard parameters of these objects. So the diameter of the orbit in astronomical units. From the Earth, of course, is at 1. The Sun is at 0. It goes all the way here to Neptune, which is about 30. The radius of those objects in multiples of the Earth. So the Sun is about 110 times the Earth. Jupiter is about 11 times the Earth, etc. Orbital period, rotational period around the axis, and what you asked about earlier, orbital eccentricity, is here the third to last parameter, and you find here the eccentricity of the Earth at 0.017. You see that Mercury is more eccentric at 0.2. Venus is much less, it's less than 1%, and Neptune here at 0.009. So the order of magnitude of these eccentricities in our solar system is about 1%, sometimes a bit higher, sometimes a bit lower. This is now our solar system, much richer than it used to be. Now, of course, we have had probes and satellites reach most of these objects, crash on some of them, even some of those moons, even some of the asteroids. There are even missions to extract gas and Earth from asteroids and bring them back to the Earth. This is, of course, after we've had astronauts collect samples of Earth from the moon on the Apollo missions and bring it back to the Earth for analysis. So we're getting much better acquainted with the planets in our solar system and asteroids and other objects in our solar system. And of course, with the Sun as well. The Dittes-Bode rule is an interesting historical story, and it goes like this. In the 18th century, people were still learning about Newton's laws and Kepler's laws and the Principia Mathematica, Newton's book, and were calculating the different distances of the planets and the periods of the planets. And they noticed that they can be shown to follow another mathematical relation. That is that if you start with Mercury and you take the distances between subsequent planets in astronomical units, or basically multiples of the Earth's orbit, they seem to follow a power law. At the time, they only had up to Uranus, but they had Mercury, Venus, Earth, Mars, the asteroid belt. Now we know that there are asteroids there. But at the time, they had a gap which they couldn't explain. But then Jupiter, Saturn, and Uranus seem to follow the same relation. So this is not a relation that tells you how each planet behaves in orbital parameters or in the relation between distance and time period, but it tells you kind of a priori where to put planets or where to expect to find planets one next to each other. And you can see that for the inner planets, this actually works quite well. The deviations are quite small if you consider where the planets actually are in relation to where this rule would have them be. Later discoveries originally confirmed this rule because people looked at where this missing planet between Mars and Jupiter should be. And that's basically the position of the asteroid belt. And they found indeed that way the largest body in the asteroid belt, an asteroid called Ceres, or Keres in Hebrew. On the other hand, when they looked on the far side with Neptune, Pluto, and other objects, it didn't play out anymore. The rule failed to continually predict positions of outer planets and objects. So this was kind of an empirical rule. Today, we actually think it's completely false, or at least we don't think it's satisfied anymore, and we don't have any physical understanding of why such a rule should even exist. So it's quite arbitrary, and it's something that seemed to work well for about 6 samples, didn't work well for 3 other samples. So we don't think it's an actual rule, but historically it was used and actually gave predictions that were confirmed. Surprisingly, it predicted the existence of asteroids. So 1801 was the first discovery of an asteroid in our solar system. It was called an asteroid because it looked like a star. What does that mean? Stars are very, very far away, so they look like points of light in the sky. Planets are close by, so they actually look like they have some angular diameter. This gets even worse if you use a telescope, and then you can enlarge planets and see more and more of them, while if you point a telescope to a star, basically no matter how good your telescope is, you're not going to see more than a single point of light in the sky. They're actually quite large, but they're very, very far away. The asteroids being quite small, when they were first discovered, no telescope could resolve an asteroid to more than a single pixel, a single point in the sky. So they were called asteroids for being like stars, like asteron is star in Greek, or the word star comes from the same root. With later telescopes, of course, now we can resolve asteroids better. So we know that a better name might be planetoid rather than asteroid, but the name stuck. And here we have the first and largest dwarf planet or asteroid or planetoid in our solar system, Ceres, presented here in comparative size to the Earth and the Moon. So we see that it's actually, in some sense, quite a small object. It's much smaller even than the Moon. But if you compare it to the Earth, it's not that small. It's maybe the size of Madagascar or a large bigger than our country and bigger than several countries. So it's quite a large rock if you compare it to things on the Earth, not very large if you consider it to other astronomical objects. Now, of course, like we said, we have much better resolution. So here we have on the left a larger image of Ceres, and we see that it kind of basically looks like the moon. It looks like a sphere, more or less. We see that only part of it is illuminated. This is similar to the moon caused by the synodic relation to the sun. So the sun here is illuminating from the right, and so the left side is under shade when this picture is taken. And we also see that the surface is not clean, it's not flat, similar to the moon. It has many craters from bombardment and encounters, basically with other asteroids. Similar to our moon, which has a very, very rugged surface, at least on the side that's facing away from the Earth, because it's constantly bombarded by other astrophysical objects, or at least has been historically. The discovery of Ceres in 1801 triggered a great interest in finding more of these. Not every day someone discovers a new planet or planetoid. And a few German astronomers collaborated together. They called themselves the Himmelspolizei, the Sky Police, and they found 3 more asteroids in the same asteroid belt between the orbits of Mars and Jupiter. The main ones called Juno, Pallas, and Vesta. We also see an interesting feature here about asteroids, which is the smaller they get, the less spherical they are. And here we have even more asteroids. There was about a period of 50 years when none were discovered, but after that, many, many more. So again, for comparison, our moon on the left in size, Ceres and Vesta, the largest ones can be compared to the moon. Then we have to go in order of magnitude smaller. So Vesta here is drawn in big, or photographed in much bigger resolution at the center. And we see an arc here of the next sized asteroids near it, and we see that they are all considerably small. The number in front of an asteroid is the number of the asteroid. Of course, Ceres is 1, Vesta is the 4th asteroid to be discovered, so it's called 4. And we see here asteroids, for example, 21, 253, and numbers going up and up. There's not really a limit or a good limit to the size of asteroids, so we don't even think that we discovered all of them. They can be quite small. If you consider here that Itokawa, in size, you have to compare it to Vesta, and then shrink that down to compare it to the moon, you realize that some of these objects can get down to the orders of hundreds or even tens of kilometers in size. So some of these objects are quite small. The reason they become less and less spherical as they get smaller is because the thing that makes basically an asteroid spherical is its own gravity, right? If you try to jump off of the Earth, you'll be pulled down by the Earth's gravity. And in the same way that a mountain will be eroded, and there's a penalty for asymmetries from sphericity because of gravity. The lower the gravity, the smaller the object, the more it can be non-spherical and have all these weird shapes. Gravity is still strong enough, though, to allow some asteroids to have their own satellites, their own moons, if you want. For example, 243 Ida, which you see here compared in size to Vesta. On the right, you see it much bigger with its own mini asteroid satellite, Dactyl, and they are gravitationally bound. So you see Dactyl is much smaller than Ida, but it actually circles Ida closer than Ida's own, in this case, long axis, because it's very non-spherical. So asteroids are a very interesting region or object in the solar system. They're small enough to be non-spherical. If they are the smaller ones are small enough to be non-spherical, they can have their own satellites, and of course there are tens of thousands and maybe more of them. Today, asteroids are interesting as sources of places to study early evolution of the solar system. They don't have an atmosphere, so not much has changed. And also with potential resources for any intraplanetary travel, because you can go on them, land a ship, and mine for minerals or precious metals or anything like that. So there's a lot of interest today in asteroids. Any questions so far?
Just a hypothetical one. If you cut a huge chunk of a continent in Earth and throw it to space, will it turn spherical after a couple of time?
That's a good question. It might take a long time. A continent might be about moon size, so it's actually, so given enough time, it might turn spherical. You'll have to see what kind of processes would actually do it. So when you have an atmosphere, it's easier to erode. You know, mountains are eroded by atmosphere, wind, and rain. That's a major effect. If you have a very low atmosphere or none at all, that's a smaller process, a smaller effect, so it would take much longer or not work. Another way you can turn a continent spherical in space is if asteroids keep hitting it. Whenever you hit something, again, you kind of spread debris, the debris will settle more or less spherically. So the moon, for example, was hit many, many times in its evolution when the solar system was younger and many more asteroids were floating around. Today, I'm not sure how long it would take a continent to get bombarded enough to actually turn spherical. It might take billions of years, and it might take even longer than that, because now the solar system is emptier than it used to be. So, but these are all questions of people who study planetary dynamics and planetary evolution actually deal with on a daily basis. What causes different asteroids to assume different shapes? What time in the history and evolution of the solar system different asteroids developed, broke apart, crashed together? How did the Earth form? How did the moon form? Today we think that actually we were once, the moon was once part of the Earth, but blasted apart when a different object hit. These are all questions of planetary evolution and asteroid evolution, and asteroids are the main, at least statistically, they give us many more examples to study in this field. Okay. So we talked about the asteroid belt, which is where most of the asteroids in the close solar system are located. Here in the white objects between the orbits of Jupiter and the orbit of Mars. But there are other families of asteroids, and there are other families of asteroids which kind of clump together and form densely populated regions in the solar system, densely populated with asteroids. And the main ones are called the Trojans, the Greeks, and the Hildas. The Trojans and the Greeks, as you can imagine, are two separate camps. They're named after the camps from the Greek-Trojan War in Greek mythology, in history. And they follow the orbit of Jupiter. So they're at the same distance from the sun as Jupiter, but they're about 60 degrees ahead and 60 degrees behind the Trojans and the Greeks. And the reason for that, again, comes from simple Newtonian mechanics. And it comes from drawing the joint potential of the two most important massive objects in the solar system, the sun, here represented in this purple circle on the left, and Jupiter on the right. Jupiter is much smaller than the sun, so obviously its gravitational effect is a lot smaller, but still it's large enough to be the two determining factors all around it. So if these lines here that I drew represent lines of equal gravitational potential or equal potential surfaces, then obviously close to the sun, they'll all be circular around the sun. Close to Jupiter, they'll be circular around Jupiter. Far away, again, they'll be circular around the total mass. But in between, you have more interesting features. you'll see that between Jupiter and the sun, there will be some point here where basically the potential gets flat. The surface of the potential gets flat, or in other words, the force drawing an object here to Jupiter or to the sun is equal. That means an object can theoretically sit here and feel zero attraction either to Jupiter or to the sun because they exactly cancel each other out. This is called the Lagrange point. The Lagrange points are the points where the potential of between two bodies flattens out. And there's, in that particular point, zero net force. So theoretically, an object can sit there, and if it rotates at the same angular velocity as Jupiter, so that it's always exactly in the same relative position, it could theoretically stay there forever. So there's one Lagrange point here in between, that's the obvious one. There's also one on the opposite side of Jupiter. You can see that as where the potential lines kind of become less and less dense. It's because the slope of the potential becomes weaker and weaker. The slope of the potential is the derivative of the potential, so that's the force. That means that there's a point here on the other side of Jupiter where the force vanishes, it turns to zero. So that's another Lagrange point. And on the opposite side of the sun as well, there's a Lagrange point. And that happens, if you remember, that they're not only the two gravitational pulls of these two objects, but there's also the centrifugal force. If this is if the system is rotating, then the centrifugal force also operates in the opposite direction. And so there are three Lagrange points on the axis connecting Jupiter and the sun. One on the other side of the sun, one on the other side of Jupiter, and one in between, of course, closer to Jupiter. Those are three Lagrange points. Theoretically, an object could sit there feeling zero force. The problem is that they are not stable Lagrange points. The potential there is saddle-like, so it's not a minimum in all directions, it's a saddle in different directions. And that means that if an object is slightly perturbed off of a Lagrange point, it will drift off either to infinity or into one of those two objects. So that's not where we expect to find asteroids, but it is still a useful, there are still useful positions to know. Every two objects basically, or if you want, every planet relative to the sun has these Lagrange points, and many satellites are sent there because the gravitational pull is very weak, and you can kind of do measurements relatively stably there. So multiple satellites are actually aimed at these Lagrange points. So these are Lagrange points 1, 2, and 3. Lagrange points 4 and 5 are in these hills on ahead and behind the orbit. And these again are points where the force balances out. Here you have to do the vector calculation with the vector pointing to the sun, a smaller, weaker vector pointing to Jupiter, and a vector pointing outwards being the centrifugal force. And if you do the geometry, the trigonometry, and you balance these three different directions, you find that there are 2 points, one ahead and one behind, which have zero net force. Those are the Lagrange points L4 and L5, and they rotate with Jupiter around the sun. And they are stable. You can see that because the potential, the equipotential surfaces kind of go around those points. So you can think of it as the top of a hill or the bottom of a hill, if you think of a topographical map. And you can have many, many stable objects around those points. It also helps, if you do the full calculation, you also need to include the Coriolis force, which means that if there's a velocity different from the rotational velocity, the force will be pushing the object back into its position. And those are the Trojans and the Greeks. The Trojans and the Greeks are asteroids accumulated in the L4 and L5 Lagrange points of the Sun-Jupiter system. Those are the stable points in the solar system, or the stable orbits in the solar system, where you can find asteroids which would live for a very, very long time without being thrown out or fall into either the sun or Jupiter itself. The Hildas, you can now see, are actually associated with L3, the third Lagrange point, the one that's exactly opposite the sun relative to Jupiter, here on the top. It's slightly less stable. The orbits of the Hildas have to obey some simple arithmetic ratio to the orbits of Jupiter, so they actually travel quite a bit inwards and outwards. They're very elliptical, eccentric orbits. But these are also kind of a camp of asteroids. You can see them in brown, extending basically in these three major areas, opposite and on the left and on the bottom. These are asteroids which basically get destabilized from one Lagrange point, go to another Lagrange point, back to the first, and kind of do this very, very long duration game of traveling between the semi-stable Lagrange points in the Sun-Jupiter system. Saturn is also quite large and has its own Lagrange points with its own Saturn Trojans and Saturn Greeks. But the main ones are these. And already we see that the solar system is much more interesting and complicated than maybe this is even new to some of you, much more complicated than what we just regularly think of as closed circular or elliptical orbits of the known planets or asteroid belt. Okay, let's take another 15-minute break and continue at 2:15. I'm still here for questions. Recording on record. Okay, so we talked about the asteroids in our solar system, the asteroid belt, Trojans, Greeks, and Hildas, and of course we mentioned earlier the Kuiper belt on the outskirts over here where Pluto still is, although it's not considered a planet. And comets are next. Comets, like we said, or guest stars or visiting stars, appear in the sky as a point of light when they're far away that moves across the sky in a very, very exceptional orbit. We typically see them when they're quite close to the sun. And of course, they don't have their own light, they reflect sunlight. So they're brighter the closer they are to the sun. We see them when they're quite close. And when they're quite close, they tend to move quite fast. But then they kind of, unlike a planet, continue on a very eccentric orbit, very, very far away. So these are typically, for anyone who's used to watching the sky, and this has been so from ancient times, they appear quite strange and exceptional. People notice them, we have records of them. Here on the right, you see a record from Babylon, the year 164 before the Common Era. And this was actually, we know now, Halley's Comet. Halley, important astronomer in the late 17th, early 18th century, was the first to actually realize that some of these guests appearing in the sky are just objects like a planet or an asteroid, but on a very elliptical orbit. And he correlated historical records and found what is now known as Halley's Comet, or 1. The first comet is numbered as 1. Here we have a picture from Halley's latest visit, which was, I think, about 30-something years ago, just when I was born, but not old enough to actually remember it, which means I might not see it again. Halley's Comet has a period of about 75 years, quite regular. And so we can correlate and see that this Babylonian comet was actually Halley's Comet. Comets, as we said, have a typically very, very elliptical orbit. Here we have a follow of Comet 55, Tempel-Tuttle, which gets quite far away. The orbital period is about 33 years. So you can expect to see it multiple times, maybe 2 or 3 times during a lifetime. Of course, the orbital period is determined by the semi-major axis, so the furthest point of the orbit. That's Kepler's third law. which means that if this comet has a period of about 33 years, we can correlate it with planets of a similar period. This would be something between the periods of Jupiter and Saturn. And so it can go from very, very close. We see here crossing the Earth's orbit, which is the blue circle close to the sun, and goes out as far as approximately the orbit of Saturn. Quite elliptical. Here on the left, comet Hale-Bopp, which has a very, very long period. Last passed here at 1997. It was very spectacular, as you can see. It could be seen with the naked eye. With any telescope, you could also distinguish between the different tails of the comets. The different tails come from different directions in which matter leaves the comet. The neutral matter basically leaves carried away from the sun, melts or evaporates and gets carried away, while the charged material actually interacts with the magnetic fields and the solar from the solar wind, and so there's slightly different behavior and slightly different angles between the different tails of the comet. This was a spectacular sight. I actually remember seeing this one when I was young, and I remember the several tens or even 100 people who committed suicide expecting this to be herald of the end of the universe. So comets are cool and also allow us to study the old solar system when it was forming, because they can come from very far away and stay very, very cold when they're far away from the sun. And so their composition can tell us something about the makings of the solar system. Okay. That basically sums up what we want to start with as basic knowledge of our solar neighborhood, what's in the solar system. But this course, of course, goes beyond that. And now we'll start talking about what's beyond the solar system and the skies all around us. And
אפשר שאלה?
Yes, of course.
אתה יכול לחזור מה זה השובל הזה שיש מאחורי הכוכבי שביט?
There are several tails behind the comet at slightly different angles. Generally, they all point away from the sun. And the reason for that is that the comet is basically dirt and ice, more or less. When it comes close to the sun, it gets hot. And so the ice melts and evaporates and the dirt gets carried away. And so particles, the comet loses mass, it loses matter. The sun, in addition to giving off light, also gives off particles, massive particles. Some of them are charged particles. We'll talk about that later in the course, but it's called the solar wind or stellar wind. You might know some of its effects when it hits the Earth. The interaction of the charged particles from the sun with the magnetic field of the Earth cause them to swirl around and create what we know as the aurora borealis and aurora australis. So the northern and southern lights, right? In Hebrew, it's called Hazohar Hatzfoni and Hazohar Hadromi. That comes from interaction of charged particles in the solar wind with the Earth's magnetic field. So when particles leave the comet's surface, the direction will depend on the same interactions. So the neutral particles and the charged particles will have slightly different trajectories. And this is similar to what you see in a charged spectrograph or a bubble chamber. If you have some elementary particles interacting with each other and there's a magnetic field, the different charged particles will curve either one way or the other, and the neutral ones will go in the middle because of the electric and magnetic interactions between the charges. So you can think of this, basically these different tails, as all being particles carried away from the comet, evaporating from the comet, carried away by the solar wind. But the difference between the different streams, the separation of tails, comes from charge separation between the different types of particles carried away from the comet. Okay, so ions versus neutral particles in a sense. Okay?
תודה.
Can I have another question?
Yes.
A bit more basic one, but what is the difference between or definition of stars, asteroids, planets?
Okay. So stars, so far we've actually mostly dwelled on one, which is the sun. Okay, we'll start the story and a bit further back. The words all come from Greek. Asteron and planet are both words in Greek. Asteron is a star, and that's basically what in Hebrew is called kochav shevet. They're fixed in the sky, they don't move, as opposed to planet, which is Greek for wander or wander around, walk around. In Hebrew, kochavei lechet, so they move. So historically, the distinction has been those which stay fixed in the sky and those which move in the sky. Now we know that the reason planets move is because they orbit the sun like we do. And so the angular position in the sky changes from day to day, so they move. The reason is that they're much smaller than the sun, and basically they're small objects. Like the Earth or like Jupiter, we have rocky planets like the Earth and Mars, or gas giants like Jupiter and Saturn. The common physical feature between them is that they're not big and hot enough to be their own source of energy through nuclear interactions. The sun is just one of the many stars in the sky. Basically, all the points of light you see in the sky with your naked eyes that are not one of the known planets or the sun are stars more or less like the sun, which means they're huge, huge balls of gas, which are dense enough at the center and hot enough at the center to produce their own energy from nuclear interactions, basically nuclear fusion. There are many more distinctions. The planets in our solar system, of course, don't produce their own light, so they only shine with reflected sunlight, as opposed to stars who produce their own independent energy and light. But that's the main distinction. It comes from size, which induces temperature, which induces energy production. The distinction between planets, moons, asteroids, and comets is a bit more shaky. There's no clear feature, right? So Pluto, for example, was considered a planet up until about maybe 15 years ago, when a new class was announced, dwarf planets, and Pluto was demoted from planet to dwarf planet. Ceres was promoted from asteroid to dwarf planet. They're approximately the same size. And the distinctions there are kind of vague. The main classification today is that a planet is considered a planet if it is large enough to clear its vicinity from any other object. So you can't have anything for a long duration around the same trajectory unless it's captured by the planet and becomes a moon. Okay, so a moon would be a rock orbiting another planet. So the Earth has one moon, Mars has two moons, Jupiter has tens of them, and Pluto is no longer considered a planet because Charon is about the same size. So it's no longer, it used to be Pluto was a planet, Charon was its moon, but now they're both kind of just dwarf planets around each other. And of course, Pluto is part of the Kuiper belt, which has many more objects which are not linked gravitationally to Pluto. So it's just not big enough to be considered a planet on its own. Asteroids are even smaller than dwarf planets. They're kind of small rocks floating around. And comets are distinguished historically just by this, by the elliptical orbit, which causes their period to be irregular, or rather to be regular and completely predictable, but you can't follow them from night to night in the same place in the sky because they move quite a lot. They get very, very far out. Those are main objects that we consider in a solar system.
Thank you.
Okay. The other stars, basically, like we said, everything in the sky that's not a planet, so most of what you see in the sky are stars. And stars are going to be the main focus of the rest of this course. So first we need to get some lingo out of the way. There are a lot of them, thousands that you can see, about 1,000 you can see with the naked eye. And of course, many, many more than that. Today we talk about 100 million stars only in our galaxy, in the Milky Way, which itself is only one of tens or hundreds of millions of galaxies in the universe. So there are a lot of them. And people from early times knew that there were a lot of them. Even 1,000 was a very large number. And of course, you can find these in biblical references as the stars in the sky, in multitude, as many as the stars in the sky, etc. And so people try to put them into some sort of order and catalogs. Constellations, of course, are one way of organizing stars. You just group them into shapes that you imagine seeing in the sky. We talked, I think, about the 12 constellations of the zodiac. We talked about the Pleiades, which is a very early constellation of stars that was documented. We'll talk about some more in the future. Another way of cataloging them is just listing those different stars by position and by brightness. And this is what Hipparchus in Greece did. Hipparchus of the island of Rhodos at 134 before the Common Era. He produced the first stellar catalog. His catalog had about 1,000 stars. And to make sense of them, he ordered them by their magnitude, or basically brightness. He started with the brighter ones, and he numbered them 1, as in the brightest. Down in classes of brightness, down to class 6, or magnitude 6, which are the stars that were barely visible to his naked eye. The Hipparchus catalog marked the positions and the brightness of these stars. How did he measure brightness? With his eye. He estimated how bright the star was. You could see a star next to other stars. You could go out at night and see, okay, what is the brightest star that I see? That will be magnitude 1. What will be the, what stars are approximately the same magnitude, approximately the same brightness? I'll put those all in category 1, in magnitude 1. The next brightest stars will be magnitude 2 and down to about 6. So his eye was sharp enough to distinguish approximately 6 different levels of magnitude in brightness of stars. If you go out at night as well, and you better not do it in the city because you won't see many, but you can also tell some stars are brighter than others. You can, even in the city lights, you can probably see at night the brightest ones. Betelgeuse, Sirius, Rigel, those are very bright stars. You can, I saw them this week with my naked eyes. You can see maybe a few tens of stars with the city lights. Those will probably be magnitude 1 or 2. If you go out to nature at night, there's no city lights and you'll see many more stars. So the stars that you can see away from city lights, but not within city lights, you can automatically classify them as being of lower brightness or higher magnitude. Notice that the scale is reverse. So 1 is the brightest and 6 is less bright than 1. So it's kind of, today would be counterintuitive, but 1 is Hipparchus marked 1 as the brightest star in the sky. The Hipparchus catalog was adopted and updated about 300 years later by Ptolemy, and of course, following Ptolemy by all the Arab world. So the Asufi catalog and the Ulugh-Bed catalog from the stellar observatory we mentioned in the first hour. The Ulugh-Bed catalog was the most important one and the most accurate one in the world, basically contemporary to Copernicus and used by Copernicus, who also had his own catalog. The first time someone superseded the Hipparchus catalog was Tycho Brahe in the end of the 16th century. He again followed many, many stars very accurately. This also enabled him to follow planetary orbits very accurately and of course, give birth to modern stellar mechanics and mechanics in modern physics, or by now, classical physics. In the 19th century, there was kind of a change to the classification system. And that was when people realized that judging by eye is not the best way to classify stars. So they defined a numerical scale. And they put the definition of magnitude on a solid mathematical footing. Basically, they realized that the human eye is actually logarithmic. So if something looks twice as bright to you, it's because your eye reacts to it, and it's actually if something looks a little brighter to you, it's actually a multiplicative factor brighter in the amount of energy that it actually produces and that reaches your eye. So the magnitude scale was adopted as a logarithmic scale, which means that they basically took the Hipparchus numbering from 1 to 6, and they said logarithmically, magnitude 1 will define as stars that are 100 times brighter than magnitude 6. So their output of energy is 100 times brighter than magnitude 6. And this basically encompasses the range of brightness that the human eye can handle, about a factor of 100 from the least bright to the most bright. Because the scale is now not just guessing by eye, that means that they divide this factor of 100 into equal jumps of magnitude 1, and a single increase of 1 in magnitude means that you take the difference between 6 and 1, which is 5 scales of magnitude, and because that's a factor of 100, then it's the 5th root of 100. So basically, an increase of 1 in stellar magnitude means a decrease in 2.512 in energy output or energy flux. And now you can actually measure quite well with a solar panel, a photovoltaic cell, or with a calorimeter, or any measure of actual energy coming in from light. You measure the flux, and you scale that relative to other fluxes of stars to get the scale. So this factor of 2.5 is basically the difference, the multiplicative difference between each subsequent magnitude. The Messier catalog by Charles Messier, Messier in Hebrew, is another important catalog. This was the time of discovery of planets, a little after Hubble, Halley's comet, and he found that there are things in the sky which are obviously not comets. They are not stars, they are not comets. He realized that there were other new things in the sky. By this time, telescopes were good enough to point at these things and see that they're obviously not comets or just regular stars. We still to this day use the Messier catalog with its numbering for many of the important objects in the sky. It was superseded by the general catalog and the new general catalog, which has even more objects which are not comets or stars. And today we call many of these objects either nebula, star clusters, or even galaxies. Many of the pictures that you associate with astronomy from the Hubble Space Telescope and other telescopes, typically would be one of either the Messier catalog or the new general catalog, NGC. And this is the Messier catalog. These are all 110 objects in Messier's catalog. And obviously you see that these are not comets and not just stars. You can see star clusters here on the top right. These are globular clusters, so they look like spheres or like globes with many, many stars all around. You can see numbers 1, 16, 17, 20, and 8. These we would call nebula because they're kind of cloud-like, they're nebulous. M1 is a very important nebula. It's the Crab Nebula. We'll talk about that and the Crab Pulsar later in the course. Numbers 57 is, I think, if I remember correctly, the Cat's Eye Nebula, so another very pretty one. Obviously, you can see 31 or M31, which is the Andromeda Galaxy. 33 is another spiral galaxy, as is 51, 66, 63, 100, 101. Many of these objects you can see. Today, you recognize these as galaxies. At the time, they didn't have this good of a resolution. They didn't have space telescopes. They didn't know what they were at the time, but they could tell that they were obviously not comets or stars, so they got their special catalog. So by this time, we had two types of catalogs. We had catalogs of stars from Hipparchus, Ulugh-Beck, Copernicus, Tycho, etc. And now we have catalogs of objects which are not stars and not in our solar system, such as the Messier catalog and the New General Catalog, NGC. We'll talk about many of these objects later in the course. For comparisons of magnitude, now that it's on a mathematical scale, we are no longer restricted to just the range of 1 to 6. We can put anything on a logarithmic scale, including the brightest thing in the sky to us, which is the sun. Here on the top left, the star, which we call the sun, our own star, is an observed magnitude of minus 26.74. I remind you that magnitude, the higher the magnitude, the less bright the star. So the lower the magnitude, the brighter it is. And obviously the sun here, the brightest thing in the sky, is about 27 magnitudes brighter than the brightest star in the sky. Every 5 magnitudes are a factor of 100. So 27 would be 5 times 100 and then some. So maybe 10 times 100 to the 5th. So that's 10 to the 11 times, if I did the math correctly, brighter than the brightest star in the sky. So the sun is obviously very, very bright, which is why during daytime, we don't see any other star in the sky. They are so dim relative to the sun. The next in magnitude is a full moon with a minus 13. That again is about 13 orders of magnitude, 13 magnitudes less bright than the sun. So twice 100 plus about maybe 10. This is something like 100,000 or something like that times dimmer than the sun. Of course, all reflected light from the sun. Some comets can come quite close, so they can be almost as bright as a full moon at their closest approach. Supernovae, like the ones we mentioned from Tycho's supernova, the first supernova documented in the West in 1572. Supernova can be bright enough to be seen even during daytime. You can see that these are quite large negative numbers, relative. Still about 10 magnitudes brighter than the brightest star. The Crab supernova was a supernova documented in Chinese and Arab sources, not in the West for some reason. In the year 1054, maybe the most famous supernova in history. We know its exact position from Chinese and Arab sources. And today we know that that supernova was actually at the center of M1, of the Crab Nebula. The Crab Nebula is basically the remnant of that explosion of the Crab supernova in 1054. Okay, so this is in the constellation of Crab or Cancer, Sartan. Constellation of Sartan or Crab. There was a supernova there, and we still follow its remnant to this day. The International Space Station is quite bright in the sky because it's very low, so it reflects a lot of sunlight, and you can see it sometimes crossing the sky. Planets begin around -4. So Venus, when it's close to us, is about -4 in magnitude. That means you can see it at night, and sometimes you can also see it just after or just before the sun rises or sets. It's bright enough. The new moon is much dimmer than a full moon, but still you can sometimes see it if you really know where to look, just after or just before sunrise or sunset. Then Jupiter, and the first star we actually see in the sky, the brightest star, at least in the northern hemisphere, maybe even totally, is Sirius, the star Sirius, which is in Hipparchus's catalog, it was the brightest as 1. Today, when we actually have a more accurate measurement, it's about 1.5. Other important systems are Alpha Centauri, we'll see that's actually the closest star system to our sun at about four light years away. So that's about minus a little, minus 0.3. Arcturus is another very bright star. Vega is a very bright star. You can see it as bright as some planets, Mercury or Saturn. Mars gets dimmer and dimmer. The Andromeda galaxy, you can see here, is much dimmer than planets, even though it's a whole galaxy. And of course, this whole magnitude that we measure, the observed magnitude, is a playoff between how much energy the star actually produces, star, planet, or object actually produces, and how far away it is from us, right? So we'll learn that some of these stars are actually much brighter than the sun, or produce more energy than the sun. But of course, the sun is so much closer to us that it appears to be the brightest thing in the sky, just by proximity, not by actual energy output. The end of what you can typically see with your eyes is somewhere around between 4 to 5. So obviously, asteroids and planets like the exterior planets like Uranus were not known in antiquity because they're too dim to be seen with the unaided eye. Everything below this line, basically, you need a telescope to be able to see. And this includes many of the larger asteroids, Ceres as a dwarf planet, other galaxies, a moon of Pluto, and things that can actually get quite dim. So this is kind of a general scale to keep in mind. Obviously, you don't have to memorize this list, but just kind of remember where different objects are expected to appear. Planets are obviously visible with the unaided eye, at least the old known planets. The new planets and asteroids are slightly beyond that. Dwarf planets and galaxies can be farther away. Major stars will be around 0 or slightly negative. And comets can, when they're close, can be quite bright, as well as some supernovae. Supernovae that are in our galaxy or close by can be quite bright. Okay, any questions?
Yeah, I have a question.
Yes.
Where do we put the scales? I mean, which is the reference point for the scale?
It's a logarithmic scale. So 0 itself is arbitrary. And historically, 0 was placed at Vega. Vega was defined as 0.
Okay.
Today, that's no longer entirely accurate. As you see, Vega is 0.03, so it's very, very close to 0, but not perfectly 0. Today, we'll just calibrate it to what people thought was the brightness of Vega at the time. But it's a logarithmic scale, so the point something something here or there doesn't really make that much of a difference. It's more for the general understanding of where different objects are located.
Okay.
Okay. So this is the Messier catalog and constellations. We already mentioned one of the oldest ways of cataloging stars was putting them into constellations in the sky. Orion is one of the oldest constellations known. It appears in basically every old civilization in the Northern Hemisphere, including our own. It appears in the Bible in multiple times under the name Xil. This here is Orion on the left, the hunter. You can tell from the 3 stars in the middle, Orion's belt, the belt of the hunter. The arm is Betelgeuse, which is a very important red giant star, one of the brightest in the sky. Rigel here on the bottom, Rigel is basically regel. It comes from the word leg in Arabic. Most of the constellation names are in Arabic. You see the hilt of the sword, and many of these known stars, you can find these with your unaided eyes in the night sky, even if you live in an urban area. Another thing we can see in these constellations is that many stars are named after the constellation in which they appear. And that will be in order of decreasing brightness. So Alpha will be the brightest star in the constellation. Betelgeuse is also called Alpha Orionis, or the alpha star of the Orion system. Beta Orionis is Rigel or Rigel. And the other arm, Gamma Orionis, some of you might know as Bellatrix, is the name of that star. The brightest star we mentioned, Sirius, is kind of trails behind the Hunter. So that's also called the dog star. It's considered to be the Orion's dog. So these are kind of old names, and we use them to this day. Many stars are still addressed by their relative brightness in their respective constellation. So you can see people studying a system called Alpha Orionis, or maybe Delta Orionis, or any of those Greek letters with the constellation in which they appear. Astronomers still use this today. Okay, we mentioned the zodiac, 12 special constellations. The only thing that's special about them is that they're more or less along the ecliptic plane. So they're important for where the position of the sun is throughout the year. And so they attracted much attention in human history, astrology, and etc. Although, of course, they're not in any other way distinct from any other constellation in the sky. And of course, a constellation is just a random assortment of stars as they appear to us in the sky. There's no actual reason for any of these stars to be anywhere near each other in the real universe, because we have no depth perception. We only know the angle to a star. We don't know how far away it is. In particular, none of the stars that we see with the unaided eye are actually gravitationally bound to each other. So it doesn't matter how close you think they look, they're actually quite far away in the sky, far enough to be really unrelated and free from each other. It's just a random angular distribution that our own human civilizations interpret. Can a star be in two different constellations? Yes and no. No, because typically when you define constellations, you would want to be specific, and it doesn't really help if a star belongs to two of them at once. Yes, because constellations have no physical meaning. They're just a way for our human mind to catalog and classify them. Then different civilizations actually had different sets of constellations. So these are the Greek Western constellations. We use them in Europe and in the Western world. These and others, but the Chinese had their own different groupings and different constellations. So they gave things different classes and different names. And people keep, when they see more stars, they try to group them as well. So sometimes people can attribute the same star to different kinds of constellations in different sets of constellations. Okay, let's say just one more thing, and then finish the class, because we mentioned distances and depth. And we said that actually we only know the angular direction to a star. We don't know how far away a star actually is. The way to measure a distance is what we mentioned a few times earlier. It's called parallax. And the idea is similar to how we mentioned calculating the distance to the moon, or even calculating the radius of the Earth, or the distance to Mars, or any of these other objects, is that if you have two base points and you look at a close object, a near star or a planet, then you can see it change angle relative to the more distant background, the really far away stars. At the most, from the Earth, we can take a parallax base of 1 year, so 2 astronomical units. And anything that's a reasonable multiple of 2 astronomical units, if we can see it, measure an actual angle, parallax angle P marked here on top, then we can calculate the distance with trigonometry as basically the diameter divided by the angle will give us the distance, or the radius. Okay, this is just pure trigonometry. The angles here are typically so small that there's no difference between the arc length and the diameter and the actual straight length. So people realized this, and they used this to calculate parallax to planets and to the moon and things like that. But from very early on, and we mentioned Hipparchus earlier, they tried to measure parallax to the stars far away, and they failed. They failed for almost 2,000 years. Hipparchus failed. Actually, that was one of the causes of the ancient Greeks to think that the stars were all fixed in position and not moving and revolving exactly around us in 24 hours because they couldn't find any depth between closer to nearer and further stars. But it failed as recently as the 18th century when Bradley tried to measure parallax to the stars, failed, but instead discovered the speed of light. We'll talk about that in the next class. A failure to measure parallax, which measured the speed of light instead. The first successful measurements of parallax were actually in the 19th century, simultaneously in the year 1833 by 3 different people, von Struve, Bessel, and Henderson. And you can see that the stars that they measured are all quite bright and quite close. Alpha Centauri is the closest one to us. Vega is one of the brightest stars in the sky, also called Alpha Lyrae because it is the brightest star in the constellation of Lyra, Hanevel. And you can see the distances are on the order of a few light years. So 4 point something to maybe 10 or 20 or so light years. For historical reasons, the unit of distance used in astronomy is not light year, but parsec, which is abbreviated as PC. It's about 3 light years. You might recall this from the Star Wars, where there was a claim that a ship can do something faster than 12 parsecs. People thought because it has the word sec in it, it's actually a measure of time. It is not. Like light year or light second, it's a measure of distance. And what is the distance? Well, we said that we can divide or multiply the angle by the distance, the radius, to find the base of the parallax. So basically 1 AU divided by the distance to a star would give the parallax angle. Alternatively, 1 AU divided by the parallax angle will give the distance to the star. Or if you want, the distance to the star is found by astronomical units divided by an arc second, or by the angle in arc seconds. Which means parsec is just a parallax arc second, and it is the distance at which a parallax of 1 arc second will be seen. So it's approximately 3.26 light years, given here also in units of astronomical units or in kilometers. You can see that it's quite far away. It's about 30,000 billion kilometers away, or 3.2 light years. And as we said, no star is actually as close as 1 parsec to us. The closest one is about 1.3. That's a parallax angle of about 0.7 arc seconds. And because these angles are so small, we understand why it was so difficult to measure them. And in fact, they were not measured until the 19th century.
So Han didn't know his units?
Can you say that, ask again?
So Han Solo didn't know his units?
Again?
So Han Solo didn't know his units?
Yes, Han Solo did the mistake of confusing time units and distance units. And it actually makes no sense to measure time in distance, because the only way to convert is using the speed of light, which is constant. And if you saw the new movie Solo, which I recommend you do not see, he actually explains it away by saying that he found a gravitational black hole he could use to maneuver to make the distance itself shorter. So they realized it upset the fans and gave this ridiculous explanation, which doesn't really help. Like everything in that movie, not worth the bother. Okay, so that's a parallax, and this is our neighborhood, our closest stellar neighborhood. Again, the sun is here in the entire solar system. Beyond the Kuiper belt, there's the Oort cloud, another cloud from which we think that comets come. And then there's this, a bit of interstellar void until we reach the closest stars, Alpha Centauri, the Alpha Centauri system, of which the closest to us is Proxima Centauri, called that because it is the closest. And you see that, again, Alpha Centauri was the first star, one of the first stars to have its distance measured. Proxima Centauri came a bit later. Now we have even newer stars at the range of 4 to maybe 6, 7, 8 light years away. our closest stellar neighborhood. As you can see, these stars are much redder and even browner. We'll talk about color of stars later in the semester. That explains why they're also much dimmer than Alpha Centauri, a bright yellow star. And that explains why we actually didn't see them until very recently and didn't know that they existed. But now we know that there are a few stars quite close by, just maybe 2 or 3 parsecs away. And we'll finish with this slide, which is just telling us that parsecs are nice and the nearby stars are nice, but they're still only an infinitesimally small part of the actual observable universe. The Hipparcos catalog, the Hipparcos satellite in the 80s produced a new catalog of stars, which can be seen from the telescope up to about half a kiloparsec away, so 500 parsecs. Newer telescopes, space telescopes like Gaia and Hubble, can reach up to about 3,000 parsecs, but that's still nothing in cosmological and universal standards. Our own Milky Way is about half a parsec in thickness, but about 50 or more kiloparsecs, or 50,000 parsecs in diameter. So we cannot even see stars to the end of our own galaxy because they're so far away. Not to mention our neighboring galaxies, the small and large Magellanic Clouds, which can be seen from the southern hemisphere at about 50 kiloparsecs. Some of these supernovae or other galaxies, which can be up to a megaparsec away. The closest large galaxies, M31 or Andromeda. And today we'll talk about the gravitational wave sources, which we can see even to gigaparsec distances. Gigaparsecs being about 3,000 or 4,000 light years away. 3 or 4 billion light years away. So the universe is actually a lot larger than what can be measured even in just parallax. There's no hope of finding angles this small with telescopes. And we'll talk about building the distance ladder all the way out to the edge of the universe further down the semester. Any questions? Okay, if not, I'll stop the recording. And